Okay, folks, today we're going to learn about forces. Japanese people are really great, and they have some funny game shows. For example, they have this one game show episode that I've seen where they roll these tires down a ski jump to see which one goes farther. Which one of these do you think is going to go farther? Well, by the end of the next few lessons, it's going to take a couple of lessons, but you should be able to answer which one you think will go farther. Let's talk about forces. A force is a push or a pull. And, we usually think of these as something that gets an object moving. And that's it. That is what a force is. They get objects moving, and it's a push or a pull. The first force that we're going to use in this class is gravity. Well, gravity is an attractive force. Attractive force, and I'm just going to write attraction. It's attraction between two objects. B/T is between, with mass. This is with. What does that mean? If I have two objects, they will attract each other and move towards each other. It's the tendency for things with mass to attract towards each other. And Einstein said this was because mass curved space-time. So objects are in space-time, and you can just imagine it almost like space, but with time. And they curve it in such a way where they create almost like little slopes and dips where objects will sort of fall towards each other, because mass introduces space-time curvature and objects will go towards each other. Point is, it's when two objects attract each other. The most common scenario is when objects are being attracted to the earth and vice versa. The earth is being attracted to objects. Now, we usually don't worry about this force right here because the earth is so massive and there's so many different objects. But gravity from the earth is always felt. We feel that really regularly, and we're going to label that F grav. F stands for force, and I write GRAV in small letters to denote what kind of force. That's gravitational force. So again, the earth and objects are attracting each other, but we really are, if we're just looking at this object, we're looking at just the force of gravity pulling the object down. And gravity will always point down in our scenarios. They will always point towards the earth. Normal force is a force usually when an object is sitting on a surface like a table, and that table pushes up on an object, and we call it normal because it's perpendicular to a surface. So let's say I have a ball and it's resting on a table. Well, the table's going to push up right perpendicular to the surface of the ball. And gravity is going to pull down. So I have gravity, and normal force, F norm, is what's holding it up. Again, if something's resting on a surface, we're going to call it normal because even if it's a curved surface, I'm going to zoom in on the ball. Wherever the table contacts it, it's perpendicular to that surface. What does perpendicular to a surface mean? Imagine I have a piece of paper and a pencil is sticking straight up out of the piece of paper. This is perpendicular. It's 90 degrees in all directions. We can also call that perpendicular to a plane, where the plane is what the piece of paper is. The next kind of force is tension force. This is a pulling force, and I want you to think ropes here. This is what ropes do. So let's say I have an object suspended from the ceiling. Well, and this is the object, gravity's pulling down, so that's F grav, and tension is pulling up. We're going to call that F tension. Every point along this rope is experiencing tension. These diagrams that I'm drawing are called free body diagrams because they're free bodies. We're just going to draw them in isolation. And we could draw free body diagrams and forces for every single point along these objects. And along a rope, every point is experiencing tension. For example, if we weren't so focused on the object suspended from the rope, we might say, what are the forces acting on the middle of the rope? Well, tension would be pulling up, and tension would be pulling down, as well as gravity. Really, we could just call it gravity pulling down, and whatever the tension going up is going to be equal to the gravity pulling down. The next kind of force is friction. Friction is a rubbing force between two objects, and it opposes motion. So whichever way an object is moving, friction will oppose it. So let's say I have an object moving from left to right across the table. Well, because it's moving from left to right, friction will oppose that motion and point from right to left. It doesn't want it to move. Let's take a look at this simulation to see how friction works. Let's say we had two books, a chemistry book and a physics book, and we zoomed in on where they're touching. Well, the two surfaces of the books wouldn't be perfectly smooth. They would have atoms and particles, little ridges and little bumps. And when they rub against each other, those little ridges and those little bumps tend to get in the way of each other. And it causes the particles to move more quickly. It generates heat. And then if you rub it enough, it starts smoothing out all of these ridges when the particles fly away. It's almost when I use a nail file to file down my nails. And believe me, Dr. Wu has some pretty nasty nails. And it takes a lot of friction to file them down. Friction is a rubbing force that opposes motion. And it doesn't always happen when an object is not moving. Let's say I have an object that is standing still and I'm trying to push on it. We would call that an applied force. That's what an applied force is. It's a pushing force. And we call it applied because an object is applying the force to another object. Well, if it's standing still, friction would still oppose motion. It doesn't want to move. So friction would prevent it from moving. So an applied force is a push, and it pretty much is any time we're pushing on objects. The last one is air resistance. And this is also a force that opposes motion. Let's say I have an object flying through the air. Let's say it's a football. And it's not just flying through empty space. There's a lot of particles in air that will push against this object. It pushes against this object, so it opposes motion. So I have to draw that force, and it's going to go exactly opposite in the direction that it's moving, and I'm going to call that either F air for air resistance or F drag. Either one is fine. People call air resistance drag. Air resistance is proportional to how big the object is. We actually call it cross-sectional area, which means if I were just looking at the object from this direction, how fat is it? How wide is it? What is its cross-sectional area? If I were looking at this tire, this is its cross-sectional area. And the bigger the cross-sectional area there is, the more air resistance there is. Air resistance is also proportional to how fast an object is moving. If an object is moving faster, it has more air resistance. Let's see how to draw some of these free body diagrams. Let's say a book is at rest on a tabletop. What are the forces acting on it? Well, if it's on Earth, we're always going to draw gravity. Let's draw gravity first. What other forces are acting on it? If it's just gravity, it would be going downward, but that's not the case. Because it's resting on a surface, there's also normal force. F norm. Those are the two forces, acting on the object. What about an egg is falling from a nest in a tree? What forces do you think would be acting on it? Well, gravity points down. Now, this is the egg. Gravity's pulling it down. That's why it's falling. But it's not just gravity. There would also be air resistance, which would act to slow it down a little bit, but it wouldn't be enough to stop the egg entirely. So there's two forces, gravity and air resistance, and gravity is stronger than air resistance in this case. What about a car is coasting to the right and slowing down? Well, coasting means it's in motion. If it's in motion, friction, we're going to assume that we're not on ice, we're not in outer space. This is the real world, and there's friction. So friction opposes motion. Is that it? No, it's not, because we're on Earth. What forces do we have on Earth? We have gravity. Is that it? Well, if those were the only two forces, then it would be moving back, it would be slowing down and moving downward. But it's not moving downward because there's also normal force pushing up on my car. What about if a car is parked on a sloped street? Happens a lot in the mountains. Well, if my street were flat, which way would gravity be pointing? It would be pointing down. Is that changed at all when my street is sloped? Does gravity change? No, it doesn't. Gravity points straight down. Well, what other forces would be acting on it to balance out gravity to prevent it from moving? Well, it's resting on a surface. So what force would that be? If you said normal force, you're right. Now, how do we draw normal force? If you said perpendicular to the surface, I just redrew the gravity because it wasn't so straight. If you said perpendicular to the surface, which would be like this, you would be right. It's exactly 90 degrees from the surface of the street. So that's normal force. But notice that if it were just these two forces, overall my object would still be traveling this direction. That's why objects roll downhill. That's how we can show the forces that cause it to go diagonally downward. But it's not doing that. It's parked. When a car is parked, what is preventing it from moving? It's the tires rubbing against the street. And so that's friction force opposing motion. So that's an introduction to not only the types of forces which we see here, but how we draw force diagrams in a variety of situations. Even when, say, an object is hanging, we could draw forces acting on all parts of an object. And using this information, we're going to begin to learn how to answer which of these tires will travel farther and fly farther. Let's go ahead and go to our practice and practice some of these things.